Okay, welcome. I'm Jeff Mosier with the National Water Research Institute, and I want to welcome you to our public meeting of our Technical Advisory Panel. And it was established for the City of Santa Barbara looking at two topics. One is subsurface intake, which is going to be the primary topic for today's session, or today's meeting. But there's also a study looking at potable reuse, and we'll have a little bit of information on that. But primarily we're going to be focusing on subsurface intakes today. And you'll get more information during the presentation. But first, what I'd like to do, because this is a little bit of a different type of meeting, is before we do introductions, just to give you a little bit of background on the purpose of what we're trying to do through this Technical Advisory Panel. So the City of Santa Barbara Public Works Department is working on water supplies options, and during this time of drought, a lot of cities around California are doing exactly the same thing, and a lot of that involves feasibility studies, looking at the feasibility of different options and different alternatives. So as part of the project, there's a technical advisory panel review, and that's the group behind me. We're going to do introductions in a minute. And what they're going to do is review the technical and scientific aspects of the work that's being done by the city and the project team related to the subsurface intakes and the potable reuse alternatives. So the Technical Advisory Panel is administered by my organization, which is a nonprofit, the National Water Research Institute. And we wanted to have a public component as part of this to be able to get stakeholder input from stakeholders on the process and what comes up as part of the review. So, we are in Southern California, but we're down in Orange County. Just a little bit about us. We have water and wastewater agency members. We've done a lot in the area of technologies, water quality, regulations, and so we tend to work in this area where we have intersection of science and how it informs policy. So we have done a lot on research project over the years, and hopefully that information gets into policy decisions. So before I get into the agenda, what I'd like to do is just do introductions of the panel and the project team, just so you know who is here in the room. So maybe, Amy, I could have you go first because you're chair of our panel.
Here we go. I'm Amy Childress, Professor and Director of Environmental Engineering at the University of Southern California. And I've researched membrane processes and advanced technologies for wastewater reclamation and seawater desalination for the past 24 years. Heidi.
Hi, good morning. I'm Heidi Luckenbach. I work with the City of Santa Cruz. I'm the Deputy Director of Engineering in their Water Department. The City of Santa Cruz started looking at desalination about 10 years ago, and as part of that process, we did very similar studies as we're talking about today. We looked at subsurface intakes and open ocean intakes. We don't have a desalination project in place right now. The subsurface intakes were consistent with what the study is with Carollo. Maybe 2 years ago, after we completed our EIR, the City of Santa Cruz City Council decided to put the desalination project on hold and instead wanted to look at other alternatives. And those alternatives are recycled water. So again, we're looking at the IPR and the DPR alternatives that the City of Santa Barbara is looking at, and we're also looking at aquifer storage and recovery. We have about 2 years in front of us to do this research. It's a very similar process, vetted by a technical working group through the community and through the governing bodies of the City of Santa Cruz.
Good morning. I'm Martin Feeney. I'm a private consultant, hydrogeologist. My experience with desal goes back into the mid-'90s. I worked all throughout the Caribbean, putting in seawater wells for ionics. Later, I worked in Sand City, developing that operating desal plant. It has a series of subsurface intakes. I more recently spent time working on the panel in Huntington Beach, evaluating subsurface intakes. I was also a member of the project team for West Basins, and I'm also a member of the hydrogeologic working group that's looking at the slant wells in Monterey.
My name is Eric Ziggis. I work for Environmental Science Associates. We're an employee-owned environmental planning and consulting firm based in San Francisco. For the last 12 years or so, I've been working for the California Public Utilities Commission, managing an environmental review process for California Americans' proposed desalination project in Monterey County. So we've published one EIR, of which I directed the preparation. We've released a second EIR, of which I directed the preparation. There's been some conflict there. As part of that conflict, the parties have gotten together and organized this hydrogeology working group, which Martin had mentioned. I participate regularly in that group, looking at the feasibility of those subsurface intakes, as well as part of the larger process, looking at other alternative intakes, as well as other potable uses and non-potable uses also in that mix in the county.
Hi, I'm Mike Wayner. I'm Assistant General Manager, Orange County Water District. I've been at the Orange County Water District for the past 25 years. Before that was with Orange County Health Department, sort of watching the things Orange County Water District was doing, including the district's involvement in potable reuse for about 40 years now, since about 1976. And in addition to what we did back in 1976, we were recycling about 10 million gallons a day of water back into the groundwater basin through injection wells to create a seawater intrusion barrier. We added considerable capacity with the expansion to the groundwater replenishment system, where today we inject and percolate 100 million gallons a day of recycled water back into our groundwater basin for drinking water supply and other uses in our service area. We are now in the process of evaluating proposals from Poseidon to come forward with a desal project that could be as much as 50 million gallons a day that the district could be the sole purchaser for, and then trying to figure out how we would put it in the groundwater basin to store it and distribute it.
I also want to introduce Gina Vartanian. She's with NWRI. She helps us capture all what occurs at the meetings, and we prepare a panel report afterwards. And Suzanne Fabel's in the back. And if you have questions about materials, you can ask Suzanne about them. She has access to the documents that we're going to be talking about today. And Tom, can we just go over from the city and from a project team point of view, who's here?
Sure. I'll let Joshua introduce himself, but my name is Tom Secord. I work with Carollo Engineers. I'm the project manager for this study project. Our team consists of Carollo, GSI, and Fugro on hydrogeological issues, DUDAC on the environmental, social issues, and Water Globe Consulting assisting with some of the global desal experience. Sitting next to me is Eric Cheresia. He's my project engineer, our project engineer for this project, and you're going to hear a lot from him coming up. So,
Great. No pressure, Eric.
Yeah.
Joshua.
Joshua Hagmark, Water Resources Manager. Here today supported with Bob Roebuck. He's our project manager overseeing this specific task. And then we have Kathy Taylor, our Water Systems Manager.
Great. And I just want to say thank you for allowing for us to use your facilities and the panel to come here. And it's been great working with you guys in terms of your preparation for the meeting. So in terms of the agenda, just want to go through this quickly. We're scheduled to be here through noon. We're going to get into the meat of what we're going to be talking about on agenda item 3, which is going to be the presentation of this conceptual design on the subsurface intakes. We're going to take questions from the panel for the project team after that, and then we're going to have an opportunity for public comments. There are public comment cards in the back. If you can fill those out and hand them to Suzanne or give them to me up front, and then we'll walk through the public comments. We are going to suggest a 3-minute limit on public comments, but that's going to be at the discretion of Amy, our chair. So if you have questions, what we're trying to do is get input from the public, from stakeholders, into the panel process so they can be considered as part of the review. So we will have just a brief wrap up and next steps in terms of where we're going to be going after this meeting. We'll adjourn at some time before noon. We will probably take in a small break at some point at some point in here, I'll just let you know that. So in terms of what else I want to go over, there is some resources that are developed as part of this process in terms of technical memorandums, work plans, that sort of thing. They are provided on the project website, or at least I should say our panel website. We're not part specifically of the project team per se. So on NWRI's website, we have all the materials, and Suzanne on our team, she manages that. So we've done the introductions. I just want to spend a little bit of time talking about our panel process. I went over it last time we were here at our first meeting, but I just want to review that quickly. Essentially, it's set up as a third-party review and evaluation, and we tend to focus on the scientific and technical aspects that are reviewed as part of the project, and then that goes into the project team for decision making. And often, as part of these potable reuse and desal projects, there are frankly tough technical decisions. Subsurface intakes is not easy. Potable reuse, although we have a number of successful examples, is still provocative. There's a lot of questions that have to be addressed from a technical, a treatment point of view for potable reuse. So often bringing in folks who've been through that type of experience and bring that into the conversation with our panel members helps be able to work through that. So as part of what we do, we document our findings in panel reports. Those are posted and made public. And eventually, we'd like to think that all this information helps make better public decisions. Okay, so at this point, we want to turn it over to the project team, and you're going to provide us a presentation on the conceptual design and other information. So Joshua, are you going to be starting off? Very good.
Good morning, Joshua Hagmark, Water Resources Manager. Thank you for everyone, panel and public are here today. Kicking off workshop number 2 for the subsurface desal intake and potable reuse feasibility study. Our agenda today will be going over the background and objectives, following up just a summary of what has happened since our technical advisory panel workshop number 1, and then handing it off to Carollo to go through the intake study, and then we will provide a small update on the potable reuse study. That wasn't the intent of today, but we will kind of update everybody on where we are with that. So, how did this get started? In September of 2014, in the midst of our discussions about reactivating the city's desalination facility, the council unanimously directed staff to evaluate the feasibility, cost, and timeline associated with both converting the offshore facility to a subsurface intake and a look at options about potable reuse. And this has kind of been a driving force. It was later connected to a requirement of our regional NPDES permit amendment. So the scope includes feasible alternatives. That's what we're developing now. We are not going to be identifying the best alternative. That's a scope of work that we would do down the road, and that would be probably attached to our long-term water supply planning. And the work plan objective, which we accomplished during the phase one, or the initial workshop, was to establish the process and criteria used for the evaluation today. The work plan had 7 sections, basically an introduction, basis of design, feasibility criteria, implementation schedule, cost estimating, methodology, feasibility analysis, and then the role of the technical advisory process. There were 3 authorizations is kind of how we broke this work up. Authorization 1 was development of the work plan. Authorization 2, which we're in right now, which is the subsurface initial screening, and then the potable reuse feasibility study. And then the work authorization 3, anything surviving the initial screening would work on, and then move forward with that. General timing, the work plan, we had our initial workshop in August. Now we're at workshop number 2 in January. The potable reuse screening discussion will be in June. And then pending outcomes from these workshops, potentially a 4th workshop in early 2017. Ultimately, we need to get back to the regional board by June 30th of 2017. We tentatively are aiming towards a May date, but at this point, the regional board hasn't published their calendar, and we'll be contacting them. I think they said in May is when they develop their calendar, and so we'll be contacting them, hoping to secure that date for 2017. So basically we received great responses to at the technical advisory panel in August. Those comments were incorporated, and we did submit that on the 31st to August 31st to the regional board for review and approval. Meantime, we awarded a contract to get Corolla moving on the feasibility work, and on October 20th, we got a official response from the regional board approving our work plan. So this turns it over. At this point, I'll turn it over to Mr. Chericia.
Thanks, Josh. So I'm Eric Chericia, again, a project engineer with Corolla Engineers, and I'm going to go through some of the conceptual design work that was accomplished as part of this study. I'd like to start with a summary of regulations that would be involved with any subsurface intake alternative. Most of this work is summarized in Technical Memorandum Number 2, which, as Jeff Mosier indicated, is available on the project website, the NWRI website. And this technical memorandum presents regulatory and permitting requirements that are associated with subsurface intake alternatives. Major permitting agencies that were identified as part of any potable or any subsurface intake study include Army Corps of Engineers, the California Coastal Commission, the State Water Resources Control Board, which includes the Division of Drinking Water and the Regional Water Quality Control Board, the City of Santa Barbara, and others. There are many environmental, regulatory, and permitting requirements for developing subsurface intake alternatives. Any one of these projects would likely include testing and data collection to optimize and recommend a full-scale project. There would be various regulatory aspects with this that could be involved. You'd have to maybe potentially drill boreholes and collect soil samples on the beach. There would be an environmental review component associated with CEQA, also containing an environmental impacts report. In Technical Memorandum 2, we identify 10 regulatory bodies and 17 requirements and permits that would be necessary to go forward with any of these alternatives. Now I'm going to get into most of the subsurface intake alternatives that were considered in our study. I'll start with the basis of design, which was outlined in the work plan, which is available on the website. Evaluating any of these alternatives, you'd have to consider design, construction, and operational criteria. Design requirements include a blend of seawater and groundwater. Any of these alternatives do have the potential to, pick up seawater and groundwater. Since any of these facilities would be located near the beach, they have the potential to be exposed to tsunami inundation, wave run-up, and coastal erosion. Also need to consider operation and maintenance requirements, periodic redevelopment for wells and drains and that are specific to each alternative, pump maintenance, especially because of the corrosion and proximity to the beach. And also we have to evaluate construction requirements such as construction area and duration that would be associated with the beach construction and some offshore construction as well. The project capacity is outlined in the work plan, and the focus of this study was to replace the city's existing screened open ocean intake. And this would be able to provide seawater for the build-out capacity of the desalination plant, which is 10,000 acre-feet per year. Thus, the design capacity of any of our intake alternatives should be 15,898 gallons per minute. And this includes a 45% RO recovery, and also includes the volume of raw water needed for pretreatment and backwashing at the plant. The site alternatives that were considered for this study include the 3 beaches of Santa Barbara, East Beach, which you can see here, West Beach, and Leadbetter Beach. These other two sites could be used for pump stations and any other facilities that would be needed. We've considered onshore and offshore sites, depending on which intake alternative we're considering. And it's important to note that any of our conceptual designs are bounded within this half-mile offshore area, and this simplifies property acquisition and also avoids crossing major faults. So with that, I'm going to actually go into the meat, which is the summary of our alternatives. I'm going to provide some brief overview of each of these technologies and go right into conceptual designs that are specific to Santa Barbara. Conceptual designs were developed for alternatives, and they were based on the greatest production capacity. And if we're unable to meet the 10,000 acre-foot production requirement set forth in the work plan, our conceptual design is based upon the greatest production capacity that is achievable. Overall, our study included 9,000 feet of beach that were available for subsurface intake development, and this breaks down to 5,300 feet at East Beach, 1,300 feet at West Beach, and 2,400 feet at Leadbetter Beach. Property was available, so condemnation of property was not required, and it's noted that all of our alternatives assume the reuse of the existing intake pipeline that goes from these alternatives to the desalination facility, so we're going to reuse that. Here's a summary of the 6 intake technologies that were considered in our study. And these technologies are based on the state of intake technology and recent studies conducted by others. They include vertical wells, onshore infiltration galleries, radial collector wells, slant wells, subsurface infiltration galleries, or SIGS, and horizontal directionally drilled wells under a patented technology known as Neodrin. I'm going to start with vertical wells. Vertical wells are similar to any other groundwater well. They consist of a pump house, a vertical turbine pump and or submersible pump, and then a casing, and then a perforated production zone where you're obtaining the water from the water body. It's very important to consider hydrologic properties with the installation of any vertical well, such as depth and productivity. It's influenced by soil transmissivity and various layers and other hydrologic properties. For a typical vertical well, you need about 100 foot by 100 foot construction area. And just an estimate on time for construction, site preparation, drilling, development, testing would take approximately 2 months per well. Each of these, well houses would also need a service facility and electrical room, and each of those would require an additional 6 months. So this is a typical cross-section of the geology in Santa Barbara's coastal region. You'll see this cross-section again for all of the alternatives that we're going to show. So I'll give you a little overview. There's 30 feet of an upper sand aquifer unit, and then there's a discontinuous clay lens that's about 30 feet below that. And then the final layer that we consider is the lower sand aquifer unit, which is about 60 feet. For the vertical well conceptual design at Santa Barbara, the well structure itself is 8 foot by 8 foot by 1 foot above grade, and the electrical building is a 12 by 24 foot building that's 15 feet tall. It's noted that for the vertical wells, the screen location is in the lower sand aquifer unit, so that's about 60 feet to 120 feet below grade. This map is what we're using to outlay our conceptual layouts for each of the technologies. I'll note some of the features of this map that will be similar and consistent with all of the other layouts that we'll show today. This green line here is the tsunami run-up boundary, so anything shoreward from this line is in the zone that's potentially impacted by tsunami run-up. This red line is that half-mile boundary off the shore. That's the boundary of our study that we must consider. For proximity, this is Stearns Wharf, and this is our existing screened open ocean intake. So here's our conceptual design for vertical wells. You'll note that the red circles show vertical wells, well sites themselves, and these blue squares are the well electrical buildings. And we've assumed, based on our conceptual design, that you can have about 3 wells per electrical facility. Overall, our conceptual design includes 15 wells and 5 electrical buildings. Wells are spaced at 600 feet and provide a total capacity of 1,400 gallons per minute. Whoa. All right. Also, I'd like to highlight on this map that construction setbacks are shown in this hatching, and sensitive habitat areas are shown by this dotted hatching. You'll see some sensitive habitat area here and here. Vertical wells are the most common subsurface intake technology that used globally for desalination facilities. They've had success worldwide in porous geologies, and it's important to note that the geology associated with site specifics is really important to see if this technology will work in your particular zone. Some global experience that's actually more local to California includes Sand City in Monterey County. This vertical well produces 400 gallons per minute. However, over some years, they've noted a well capacity has been reduced by 50% due to plugging and fouling. Marina Coast Water District, also in Monterey County, produces 400 GPM. Although no operational data has been provided to us, it is threatened by coastal erosion. Morro Bay uses 5 beach wells to provide a total capacity of 850 gallons per minute. In this particular installation, they note high iron concentrations, which mandates the need for pretreatment at the desalination facility to avoid fouling of your RO membranes. Here are some conceptual design considerations that resulted from some of the technical analyses we performed as part of this study. It was determined that this technology would impact our shallow groundwater. It would impact sensitive habitats. It has the potential to mobilize contamination that's already in the groundwater, the upper zones. The facilities are susceptible to tsunami, inundation, and erosion, and there are impacts by sea level rise that were noted. Next, I'm going to go on to lateral beach wells, otherwise known as onshore infiltration galleries. Onshore infiltration galleries and subsurface infiltration galleries are very similar in their construction, and the difference between these two is the location. Lateral beach wells are installed onshore or in the surf zone, while the subsurface infiltration gallery is installed several hundred to 1,000 feet offshore. As I mentioned, onshore infiltration galleries are similar to configuration and operation as subsurface infiltration galleries. They consist of an engineered filtration bed. They've been successful in small projects and are often used when the offshore conditions where you'd install a subsurface infiltration gallery are infeasible. Compared to the subsurface infiltration gallery, the onshore infiltration gallery requires 30 to 35% more area and does have more freshwater impacts being closer in proximity to the shore. Proponents of this technology indicate that the technology is self-cleaning. However, backwashing and chemical treatment may be needed. And it's estimated that this technology would take about 2 years for construction. Here's a cross-section of the onshore infiltration gallery. You can see the collection vault in which all of these laterals and drains drain into this main collection vault. The pump station building is 24 by 24 feet and is 15 feet high on the beach. You can see from this technology that we're deriving water from the upper sand aquifer unit as the drains are placed at a depth of 30 feet. And overall, you need 4,500 total feet of drains. Here's a conceptual layout for the onshore infiltration gallery. We're noting that this technology was determined to be infeasible at East Beach due to sediment transport and coastal hazards evaluation that we're going to present later. This technology was feasible at Leadbetter, but problematic to construct due to the high energy wave environment in this area. And then there is one onshore infiltration gallery that was installed here at West Beach. There's a total of 3 galleries that provide 5,000 gallons per minute of total capacity. Worldwide, there are no onshore infiltration galleries matching the size and complexity that would be required for Santa Barbara. A relevant example is the Alicante 1 seawater RO plant that's in Spain. This facility provides 2,100 gallons per minute of capacity and is installed in a highly porous limestone formation, which is different than the geology of Santa Barbara. This particular installation shows lower water quality with a much higher turbidity and silt density index compared to vertical wells. Silt density index is a test that's typically performed for RO membranes, which evaluates the need for pretreatment. These two figures below show a silt density index test, and this is filter paper from the Alicante vertical well and the onshore infiltration gallery. You'll note a much higher fouling potential here and turbidity. It's clearly seen from these photos. Some conceptual design considerations associated with the onshore infiltration gallery. Our results show that this technology does have the potential to impact shallow groundwater, does have the potential to impact sensitive habitats, and potentially mobilize contamination. The beach facilities are susceptible to tsunami inundation and erosion, and the facilities are impacted by sea level rise. Moving onward to the radial collector well. Radial collector wells are similar to groundwater wells, and the main difference here is that you have these laterals that extend outward into the sea, towards the shore. The advantage compared, these are used compared to a traditional vertical well because you can increase your production per facility because you're placing these horizontal screens in the most productive zone of the aquifer. Individual wells are designed to produce between 1 and 5 million gallons per day, which is 700 to 3,500 gallons per minute. Here's a cross-section for the radial collector well established for Santa Barbara. You'll note the 150-foot setback is the distance that you must maintain to avoid susceptibility to coastal erosion. The well structure is here. It's a 20-foot diameter building that's 15 feet above the ground. This is the caisson here in which the water from these radials drains into, and then a submersible pump will transmit it out and to the desalination facility. This technology derives its water from the upper sand aquifer unit, and the radial screens are placed at a depth of 30 feet below grade. Here's a conceptual layout for the radial collector wells. You'll note there's 15 wells total at a spacing of 600 feet for a total production capacity of 5,600 gallons per minute. Radial wells require close proximity to the shore to derive primarily seawater, and one of the most important considerations with this technology is sediment transport. Salina Cruz, Mexico is the only installation worldwide that uses this technology as an intake for a desalination facility. At this installation, 3 wells deliver 3.8 million gallons per day, which is around 2,600 GPM each. This installation has shown beach erosion and reliability and environmental problems. Since its installation, there's been a 20% decrease in production. Seawater intrusion has occurred, and they've experienced a complete drainage of nearby coastal wetlands. These figures below show the importance of sediment transport studies and coastal erosion studies. This is 1 year after installation. You can notice the beach erosion starting to erode some of this caisson. And after 4 years of installation, you can see the erosion is swept away, and there's actually water and tide inundating the facility. Like many of the other technologies we've considered, radial collector wells require access for operation and maintenance. This is a figure depicting a typical installation on a beach. You'll note the access road that's needed for service vehicles and access. These Most of these facilities are 15 or more feet high to avoid potential for run-up due to coastal and seawater. And typically, there will be a security fence to keep these facilities secure. Conceptual design considerations for the radial collector well. It was determined that there would be a potential for impact to shallow groundwater, potential impact for sensitive habitats. These facilities can be impacted by contamination that is in the area. Beach facilities are susceptible to tsunami inundation and erosion, and it is impacted by sea level rise. Next, I'll go into slant well conceptual design. Slant wells are subsurface intake wells that are drilled at an angle to maximize seawater collection and reduce impacts to coastal habitats. Actually, this drill rig will drill this at an angle between 20 and 45 degrees from horizontal down into an area that's below the seafloor, where the hope is to infiltrate water from the sea. This technology offers natural filtration by ocean floor sediments. Construction of this process is very similar to vertical wells, although specialized drilling equipment is needed to drill at an angle. Here's a cross-section that shows the slant well conceptual design at Santa Barbara. You'll note again the 150-foot setback to minimize coastal erosion. Each of our facilities, you'll have a collection vault and a slant well structure that's 24 feet by 30 feet and is 15 feet high. And each facility includes 2 slant wells that are drilled at an angle outward from each other. So you'll have two slant wells per site. You'll note that the screen location derives its water from the lower sand aquifer unit, and the screen itself is 175 feet long. The conceptual layout for the slant wells has a total of 16 wells, and this is at 8 sites. As I mentioned before, there are 2 wells per site drilled at an angle. Each of these slant well sites must be spaced 650 feet apart, and the total production capacity of this system is 4,400 gallons per minute. Although no full-scale installations exist, several test facilities have been constructed. In Dana Point, California, a slant well test facility was constructed, and they note that their system is currently producing a water source that's about 50% seawater, although modeling suggests that the percent seawater may increase over time. In this installation, there's high iron and manganese, which requires pretreatment to send to an RO desalination facility. Also, this installation is noting very low dissolved oxygen, in which you must treat the brine before discharge back into the ocean. Drilling and testing is ongoing at a test facility in Monterey, California, although the current test demonstrates that they're receiving approximately 90% seawater from this installation. Conceptual design considerations noted from our analysis show that there is the potential to impact shallow groundwater, there's a potential to impact sensitive habitats, there's a potential to mobilize contamination, beach facilities are susceptible to tsunami inundation and erosion, and these beach facilities are impacted by sea level rise. Next, I'll go into the subsurface intake technology, known as the subsurface infiltration gallery. Subsurface infiltration galleries are engineered slow sand media filtration beds that occur at the ocean floor. As I noted before, this technology is typically several hundred feet to 1,000 feet offshore, and they're primarily used when horizontal and vertical wells are infeasible, as they are offshore. They're sized and configured using slow sand filtration design criteria that you'd use at a conventional water treatment plant. And this technology relies on wave action and currents to remove solids from the filtration bed, so they actually are self-cleaning. Construction of a subsurface infiltration gallery is more complex than any other subsurface intake alternative. There's various alternative ways that you could construct these. What we're showing here is a permanent trestle used for the offshore to access and maintain this structure. You'll note a large area here for construction staging that's on the beach. This technology was evaluated as part of the Huntington Beach Desalination Facility project, and they had an independent scientific technical advisory panel. And this project also recommended the construction of a permanent trestle to provide a long-term maintenance strategy. Construction impacts associated with the installation of this technology may include loss of marine life and habitat within the footprint of the infiltration gallery offshore. Because of this large laydown area, there's limited public beach access, and dredging this large amount of sediment to install the filtration bed would require dewatering and disposal. The increased truck traffic during the construction phase would increase greenhouse gas emissions. This slide presents several of the methods that would be utilized to install a subsurface infiltration gallery. Because of the high energy wave environment of the offshore of Santa Barbara, a traditional barge would not be able to be used to provide a stable base to do the dredging and bed installation. For that reason, there's a potential to use what's called a jack-up barge, where this barge is actually jacked up out of the sea to provide a stable condition for construction. However, because this technology would be providing a water source for the city's desalination facility, it is recommended to use a permanent trestle to provide maintenance over the course of the installation and the operation of this intake technology. As an alternative, other installations, this is a photo from Long Beach, shows that you could actually have a sheet pile to drain all of the water in the nearby to install the filtration bed. Global experience associated with the subsurface infiltration gallery indicates that there may be long-term performance issues. Fukuoka has a subsurface infiltration gallery in Japan that provides 9,200 gallons per minute from 5 acres of filtration bed. It has been in operation since 2006, and since then has seen a capacity reduction of 25% that is attributable to biological fouling. Long Beach, California installed a test facility. This photo here shows a cartridge filter after 1 week of operation at a seawater RO membrane plant. For reference, a traditional RO facility, you must change these cartridge filters about every 2 months. And in this particular installation, you're seeing cartridge filter replacement weekly. Through our analysis, we've determined that construction of the subsurface infiltration gallery at any of the project sites is infeasible. At East Beach, stable sediment transport conditions are not achieved within the half-mile area offshore. In fact, this area where you would be able to install the subsurface infiltration gallery is noted about 8,000 to 9,000 feet offshore, which is well outside of the boundary of the city-owned lands. At West Beach, construction activities would interfere with harbor use and navigation. Also at West Beach, installation of the subsurface infiltration gallery would require crossing the Rincon Creek Fault. At Leadbetter Beach, stable sediment transport conditions are not achieved within the half-mile area offshore, and the installation at this beach would also require crossing the Rincon Creek Fault. Finally, I'm going to go into a conceptual design of the horizontal directionally drilled wells. Horizontally directional drilled well intake systems consist of drains extending seaward from the shore. The directional drilled apparatus here directionally drills some distance seaward, and in traditional installations, you're drilling through, you must daylight the drill, and then you pull an HDPE pipe through, and this production zone of this intake is actually a porous special filter pipe that you're deriving the water from. Traditionally, these systems consist of a common wet well where numerous drains drain into. and each collector well pipe yields between 800 and 2,400 gallons per minute, depending on your particular hydrogeologic conditions, site-specific. Here's a cross-section of the horizontal directionally drilled well. You'll note a pump station building with collection vault that is 24 feet by 24 feet and is 15 inches or 15 feet tall. As with other technologies, you must have a 150-foot setback to negate the coastal erosion. This intake technology is deriving from the upper sand aquifer unit, and the drain screen length is 1,000 feet. The conceptual layout for the horizontal directionally drilled wells is at East Beach, and it consists of 11 drains total feeding into one site. Each of these drains is 1,500 feet in length, and the total production capacity is 15,898 gallons per minute. This technology has been used for 10 years as an intake technology in Spain and has seen performance and reliability variability. The largest installation is at the San Pedro del Pinatar plant, which is in Spain. 20 wells are placed in a fan shape that provide a total capacity of 11,800 gallons per minute. This installation has encountered several technical issues and limitations. 4 wells lost over 40% capacity over 9 months. Currently, other wells are losing capacity, and new wells were needed to restore plant capacity back to the design capacity. This plant is going through a second phased plant expansion in which the owners have elected to use a screened open ocean intake instead of the horizontal directional drill technology. Other considerations for the horizontal directional drilled system include specialized equipment and materials that are required. In fact, you must stabilize the borehole as you're drilling with a pressurized, you must pressurize the borehole, stabilize it, and use a drilling fluid coating for further stabilization. As I mentioned previously, the conventional horizontal directionally drilled systems require daylighting the drill offshore, and this has the potential for a drilling fluid release, which would require mitigation. New technologies have been proposed that claim to avoid drill daylighting. However, no successful installations are seen to date. Design considerations for the horizontal directionally drilled wells are seen in this layout. The system is not expected to impact shallow groundwater and is not does not also impact sensitive habitats. There does not appear to be a potential for mobilization of contamination, although the beach facilities are susceptible to tsunami, inundation, and erosion. The beach facilities are also impacted by sea level rise. With that, I'm going to turn it over to Tom, who's going to go over some more supporting technical analyses that were part of this study.
So Eric has provided us some of the kind of summary backgrounds on what the layouts would look like based upon the basis of design criteria and the methods that were called out in the work plan. We wanted to present just a little more background into some of the technical studies that supported those layouts before we go through the initial screening process. So first, we're going to talk about sediment transport and coastal hazards. There was a full report that's provided as an appendix to Technical Memorandum Number 3 that's available on NWRI's website. We hired a oceanographer that's done a number of these studies, and these studies are typical and required for most coastal development permits through the California Coastal Commission. And this fellow that we've hired, Scott Jenkins, has done quite a few of these in the past. So the purpose here is to address each beach in the study, and we're looking at just normal sediment transport characteristics and then coastal hazards associated with or tsunami, inundation, sea level rise. Summarizing the sediment transport analysis for West Beach, we find that the onshore infiltration gallery is potentially feasible, but due to the types of sediments that are typical to, this is the harbor area, very fine sediments, the sediments for this type of intake would lead to plugging and fouling that would require some routine maintenance. So still potentially feasible, but would require maintenance. West Beach, therefore, cannot sustain reliable production without that type of maintenance. The further offshore you go with subsurface infiltration galleries and HDD collector wells, there isn't really, particularly for the HDD collector wells, a way to do any maintenance on those facilities. So plugging in that case would lead to a loss of the facility. Looking at Leadbetter Beach, it's feasible for the onshore infiltration gallery and the subsurface infiltration gallery. I guess I should point out that we're focusing here on offshore alternatives. Some of the conclusions for sediment transport are applicable to onshore, but coastal hazards and sediment transport we're presenting here are just the offshore portions. But anyway, we're feasible for the onshore infiltration gallery and the SIG. There are some operational challenges associated with high energy wave conditions seen at this beach. But as Eric had presented, we don't have a stable ocean floor within the half-mile boundary. It requires a depth of about 70 to 80 feet before you find that stable conditions, so we don't have to worry about daylighting the subsurface infiltration gallery drains. So for that reason, because we're not within the half-mile boundary, the subsurface infiltration gallery is not feasible. It is feasible for the horizontal directionally drilled well, however. With East Beach, we found that it was not feasible for the onshore infiltration gallery and subsurface infiltration gallery, the SIGS, due to the periodic sediment transport conditions. If you were to walk on East Beach right now, you would see there's an old hydraulic structure for the city's old outfall that is just exposed in terms of all the rocks surrounding the outfall pipe that pass in and out of that outfall. It's a weir box structure. So, I mean, you could imagine any sort of gallery type structure would be periods of exposure of the drains and then periods of deposition of on top of the drains. However, the coastal erosion and coastal hazards analysis did find that there would be an appropriate depth for installation of these horizontal directionally drilled drains as a viable option off of East Beach. So just concluding here, for erosion, for any onshore facility, periodic erosion, we found that a setback of 150 feet was necessary. So any buildings, vaults, needed to be 150 feet back in order to prevent that sort of periodic coastal erosion hazard. That doesn't necessarily apply to tsunami type of induced erosion, but the HDD drains, in terms of erosion, would be unaffected at a depth of greater than 12 feet below what's considered a stable depth. So we're still within the 30-foot lens of material that's available offshore. Sea level rise, none of the onshore facilities are flooded by wave run-up at the present sea level conditions with that 150-foot setback. But part of this analysis and part of the way that a standard coastal development permit, coastal hazards analysis would look at it, it asks for a 50-year evaluation of sea level rise, and all of the facilities onshore would be threatened at that 50-year condition. So, and for the tsunami run-up, Eric had shown a graphic with the green line. Those are the present day, the 2015-2016 tsunami hazard area. With sea level rise, that area would grow, but basically all of the onshore facilities would be inundated by tsunami events. Wanted to briefly go through some of the hydrogeological analysis that GSI and Fugro had supported for us. In the technical memorandum, I'm not going to try and go into this table very much. I'll highlight one portion, but this summarizes the yield, the facility spacing, and the length of beach required for, here we have all of the different types of intakes, and you got a number of facilities, spacing, linear feet of beach required to produce the target yield of 15,000 gallons per minute. And then what yield is available from each facility. But focusing in here, what we found is that, coastal hazards aside, so the SIG, we were not able to put any SIGs on East Beach, or actually anywhere. Conceivably, we could achieve our target yield of 15,898 acre feet with both the horizontal directionally drilled weld and the SIG alternatives. But none of the onshore alternatives were able to meet the target yield. With the onshore alternatives, we found that the objective here was to model this at a maximum production rate. Certainly, we could decrease the production rate to fix this problem that we're seeing here, which is impact to sensitive habitats. So at the maximum amount of yield that we could achieve, these are the types of drawdowns that we would see in our sensitive habitat areas. But again, with SIG and the HDD alternatives, we found that we could put those facilities far enough away so that we're not impacting shallow groundwater supplies. Thinking about shallow groundwater supplies, there's potential to capture known groundwater pollutants, 75 contaminated sites within the study area, as well this area of town that we're looking at as a result of the 1925 earthquake. A lot of the rubble from that was placed in this area. So while there's 75 known areas of contamination, there are other areas that are potentially contaminated within this study area. So only the SIG and the HDD alternatives avoid mobilizing or potentially capturing any of those types of groundwater contaminants. So we were, after going through this technical analysis, where we're looking at the various alternatives, the basis of design and the conceptual designs, we need to go through our initial screening criteria, which was defined in the work plan. And as called out in the work plan, there were a number of different criteria, and these are typical to the types of criteria that are called out in the new California Ocean Plan amendments, desal amendments. Geotechnical hazards, hydrogeologic factors, benthic topography, oceanographic hazards, presence of sensitive habitats, and design and construction constraints. And this approach was approved by the regional board in their October 20th approval of the work plans. So this is a two-part slide. We've got 12 different criteria, and you'll see that these are also handouts that are available in the back of the room, but we have the various, so we've got geotechnical hazards, hydrogeologic factors. Those are the criteria that were called out in the California Ocean Plan amendments and in the work plan. And within the work plan, we also broke down what it means and how to define these various conditions so that we could evaluate potential feasibility, non-feasibility, and then we added a criteria as a result of our last workshop and the comments that we received that was potentially feasible but doesn't meet the study objectives. And in particular here, it's about the yield. So while all of the onshore options didn't meet the yield alternatives, it's possible that we could consider them again in the future if we were to redefine the study objectives. But so for the purposes of this project, we just call them potentially feasible. PF stars, potentially feasible, doesn't meet the study objectives. So looking at this slide, we'll see there's a few not feasibles, and then the HDD wells are potentially feasible on this slide. Oops. Going to the next slide, we see some more not feasibles and another not feasible, this time in the HDD well category. As a result of the initial screening, none of the alternatives were passing the initial screening review. So if it is not feasible in one category, this is technical feasibility, they're not feasible. So looking at this, the HDD wells passed all the initial criteria except for number 12, and this is precedent. And this is based upon the fact that there is no California or U.S. experience. There is, however, 10 years of global experience. And with that 10 years of global experience, what we see is inconsistent performance, so reliability of the drain technology. So the not feasible conclusion for this study is supported by the independent science technical advisory panel process that was assembled by the California Coastal Commission for the proposed Huntington Beach desal facility. And this, as well, is supported by the experience at this San Pedro del Pinatar facility in Spain, where they saw loss of capacity and poorer than expected water quality. And as a result of that initial performance, when it came time to expand the plant, they expanded with a screened open ocean intake. So subsurface desalination intake technology, summary of our study. None of the alternatives passed the initial screening. One alternative was constrained by seismic or oceanographic hazards. 4 of the alternatives were not feasible as a result of impact to sensitive habitat areas, and then 5 of the alternatives had design and construction constraints. The HDD well technology is continuing to be developed, and the city and the California desalination industry as a whole should continue to follow this type of technology. In particular, there's a pilot test that's being constructed currently by the San Diego County Water Authority at Camp Pendleton. So the industry should continue to follow this technology to see if the reliability aspects can be improved, can be addressed. So that is a summary of our subsurface intake study, and we wanted to give you a status update on our potable reuse study before we turn it back to the panel and the rest of the agenda. So for the potable reuse study, technical memorandums 1 and 2, which are an introduction and then a review of the regulatory and the permitting process, those have been completed. They're posted on NWRI's website for everybody to look at and review. The groundwater modeling and the conceptual design is in progress, and we're collaborating with the USGS, who is doing the groundwater modeling work for our team. We will continue to develop these alternatives in a similar manner where we've got the conceptual designs, the layouts, and these sorts of technical considerations that were called out in the work plan. We'll have our next presentation on that portion of the work in Workshop 3 with this panel in June, tentatively set for June 29th. So with that, I'll turn it back to the panel.
Okay, thank you very much for the presentation. We will open up to questions, but before we do, we'll take a 5-minute, very short break. Okay, if everybody would take their seats. The social break.
Get your team back together.
Yeah. Well, I told you. Okay, we're ready to get started. I don't know if I'm allowed to use that. Okay. Okay. Okay, so if you do have public comments, please turn them in to Suzanne, who has been standing in the back of the room. I'm not sure where she is right at this moment. Oh, there she is. Okay, so first what I'd like to do, though, is open up questions from the front. Any questions?
Well, the panel.
Yes, from the panel. Sorry.
Yeah, a couple questions. I'm going to look to your slide. I can't see the number. It's the basis of design subsurface intake slide. Was it 14, perhaps? You talked about design requirements being blend of seawater and groundwater. 14. There, that one, the design requirements, blend of seawater and groundwater. You used it as a criteria, for evaluation, but you used it as a design requirement, is what it says here. Can you just clarify how this was used on the design side?
So I guess this was one of the issues that we ran into with the work plan, was that we had conflicting goals. We had optimized the capacity, and we also had issues with, well, if you reduce the capacity, you can minimize your impacts to the groundwater, reduce the impacts to the sensitive habitat areas. And I guess without defining a new criteria that wasn't within the work plan, like quantify what is de minimis impact for impact to groundwater, what is de minimis impact for impacts to sensitive habitat areas, we really couldn't address those sorts of modeling scenarios. So we chose to go with what is the most that you could produce, and we could define what the impact was with influence to groundwater, influence to sensitive habitats. And then if we chose to live with those sorts of impacts, we know what the answer is, what this is the most that we could do. Or if that was too much, we could then, in a later study, define what the de minimis impact would be.
And you made the point in the footnote in the document that was, we could go through that, but we need to prove de minimis if we're going to go there.
Right.
Right, okay.
Moving on, for me, it's just a language issue, because it almost states that that's what you're looking for, meaning you're looking for a blend of groundwater and seawater, and obviously you're not if you're talking about SIGS.
Right. Yeah.
So
we want to know what with the goal being what is the most we can produce. What is the answer in terms of this impact to shallow groundwater? What is the result in terms of impact to sensitive habitats? So we can refine that in a later study for these alternatives. But I think that, looking at the answers here, none of those alternatives are going to really fully meet the overall production goal, whereas the HDD drains and the SIG alternatives could. So if the objective in the future is what do you need to do in order to move away from the screened open ocean intake altogether, we have an answer for that. We have a path toward getting to an answer if you were going to put in one one vertical well to reduce the flow from the open ocean intake by one vertical well. We have a path towards defining the issues for a later study. So
You could
What?
set the range.
I think there's a lot of space on that thing. I think there's too much embedded in that one first bullet. Meaning, maybe you should just say, minimize or balance on-land impacts with, seawater, except the fact that we may get a blend. I think there's just too much in that one. It's not real clear what you mean. Like, we're trying to get a brackish water, but then again, you're looking at SIGs that obviously are not, So like I said, I think there's just too much trying to be said in that one bullet.
okay.
A couple more slides. This is 14. If we could move to 18, you showed the 9,000 feet of beach available for subsurface intake, and I guess my question is that calculation with or without the exclusion zones?
So that 9,000 feet is available beach for development. It doesn't include the areas that you cannot construct on.
Netted out the exclusion
Netted it
zones.
out, yes.
Okay. It's just a consistency comment I would make on maybe 19. The next slide is when you start talking about the onshore infiltration galleries. The report refers to them as beach infiltration galleries. They're BIGs and SIGs, and here you've introduced a different term than what we had in the document. So for consistency. And on, if that is 1924, it's the lower right-hand, the impact by sea level rise. I didn't see, Tom, in your discussion, you did talk about the beach hazards and the 7 to 35 inches of sea level rise, but it was all about wave run-up. It doesn't really say anything about sea level rise. It talks about wave run-up, and you've included sea level rise in that wave run-up. Do we know where the shoreline will be in 50 years? Did Scott do any of that to define where the shoreline would be?
I'd have to look back at the coastal hazards report.
Because I know he included the sea level rise as part of the wave run-up side of it, but I wasn't sure if there was ever a redefinition of what your shoreline might be.
Yeah. I'd have to look back.
There's a recent USGS study on Santa Barbara that does look at where the shorelines are going to be. I can send you that reference if you need it.
Please.
26, can we jump to 26? Small projects, successful in small projects. How do you define small projects? I'm at your second bullet. Is there a capacity size where you define small?
We need to define that better.
I just don't know, yeah. It's totally judgmental, so if there's some, okay. I don't know what slide it is. You talked about the slant well conceptual design. So if this is, it's after the slant well layout. It's the, I just want to make one more. Maybe another one. This one. I just want to point out that in Monterey, the current testing at the slant well is demonstrating they've achieved, I think it's 94% seawater as of last week.
Really?
Yeah.
Well, that's news to me.
Yeah. So that is continuing to climb. Okay.
Well, since we're working on some of these slides, back to the slide that talks about Marina and Sand City, I can add some clarification. There's a bunch. See, in the report, you talk about the Sand City plant being a 0.6 MGD plant. It's actually a 0.3 MGD plant with two redundant trains. Okay, and so it was always designed just to be a 300 acre-foot plant. They do have well capacity issues. That's true. And Marina Coast, me and Robert Marks, who's in the back of the room, built those wells. It made like 500 gallons a minute. They ran it for about 2 years, and you're right, it's falling in the ocean. They destroyed the well. But so.
Do you have anything between here and where we were?
Excuse me?
Do you have anything between here?
No, I don't think. I don't.
Jump back to, if you could, back to where we were. Slant Well's conceptual design considerations. You've got the map and this one. You articulated differently than what the words say. You articulated differently than what the words say, and your articulation, I think, was a better framing of this issue. You said it mobilizes contaminants, and that's really what you're doing. It's not really impacted by the contaminants, right? It's how this affects the environment, how the environment would affect the project in this case, right?
Correct.
What's the nature of the contaminants we're talking about? What kind of contaminants are we describing?
They vary. For example, at some of the sites there are hydrocarbons and lead, and
This is from fuel sites, basically from gas station leaks near the shore?
I don't recall any fuel station sites. There are rubble from the 1925 earthquakes, and within that rubble, there is hydrocarbon and lead associated with the rubble.
So some of them are contaminants that you might have difficulty removing with reverse osmosis, like some of the smaller hydrocarbons. The lead, not so much of an issue, but then it's more a matter of whether it's mobilizing contaminants to move in ways that they wouldn't otherwise. Okay.
Correct.
Okay, thank you.
One more thing on the rainy collectors. Why did you select a lateral length of? I don't think it'll make a difference in analysis, but they can advance at laterals like 300 feet, and so you could have 300-foot laterals, 3 of them pointing out, and they would actually get under the ocean, which would so.
I think what information we had from our hydrogeologic team was that the construction experience at the longer depth was less than a more standard length of 150. So, and I've read too that the length is varied between, like, I've not heard 300 feet. I've heard more like
Rainey will sign a contract to advance it 300 feet. They won't sign a contract to go further.
Is it dependent upon the type of media you're drilling through?
Well, of course. I mean, they're going to do their exploration first.
Yeah. So.
But if you're at a conceptual level, you can make.
And maybe that was part of the feedback that we got from the hydrogeologic team, was that with the unconsolidated sand media that we have, I don't know. We can ask them. We can ask them to qualify the depth or the length.
Typically, in practice, they're in unconsolidated gravels.
Right.
I mean, that's the whole nature of them. They're drilled reverse, so.
Mm-hmm.
Okay, good. Any other questions from the panel? All right, Jeff.
So public comments. So we just got 3. If you had a public comment, if you want to fill out a card, it's not too late. Give it to Suzanne. So we'll go by the order that they were provided. The first is Dr. Ido McGowan. Ido?
Good morning. Thank you for allowing this. I'll read this. My interest is public health, waterborne disease, contamination, and particularly of interest is the nanocontaminants, the formation of biofilms, and gene transfer. Use of recycled water is in our future, but, and that is a big but, if the Johnson Space Center is having problems with recycled water with all their staff and funds, and the state's expert panel excused itself on the topic of antibiotic-resistant bacteria and their genes, it seems that there are unanswered questions. The city, in its analysis, evidently ignored these critical aspects. Current water treatment for recycled water no longer adequately protects the public health. The finished and disinfected recycled water remains to be a risk. There is substantial evidence of serious emissions by the city in looking at this. We previously submitted a robust file of peer-reviewed studies showing adverse impacts to public health from recycled water. That's as it is now produced. The city's comments indicated that our comments were beyond the scope of the program. And we are on camera before the public, and so it would be interesting to entertain asking the city whether or not they could explain that comment. We need to review small particles, antibiotic-resistant genes can pass through a 2 nanometer pilus, which is between transmitting and receiving bacteria. So we need to think about the filtration systems that would be able to handle that. And I'm not sure any of that was even considered in the recent EIR. I don't think it was an EIR, I think it was a negative deck that the city produced for its expanded recycled water plant. And I think that's where we need to go back, is review those data, because by ignoring that, they have an incomplete document. Thank you very much.
Okay. Next is John Ackerman.
Ladies and gentlemen, both Dr. McGowan, a retired hydrologist, and myself, a physician, also retired from my practice, was changing my parking space while didn't have a chance to introduce what Dr. McGowan had to say. And I think what he has said is quite sufficient about our concerns, and I will leave it at that.
Okay. Thank you. Kira Redmond with Santa Barbara Channel Keeper. Kira?
Good afternoon. The Santa Barbara City Council's directive for these studies was to explore a range of alternatives, including subsurface intake and potable reuse options. The Regional Water Board's directive was to analyze the feasibility of a range of alternatives, including subsurface intakes and potable reuse options. These directives in no way direct the studies to evaluate only a complete replacement of the open ocean intake, nor only to produce more than 3 times the water the city intends to produce. Unfortunately, that leap was made and framed the analysis of feasibility. I voiced the concern about the 10,000 acre-feet per year capacity threshold for these studies at the initial meeting of this panel last August. That concern was echoed by the Regional Water Board in its October 20th, 2015 letter to the city. However, those concerns were ignored, and the study proceeded to use this 10,000 acre-foot threshold, thereby all but ensuring that the subsurface intake alternatives would come out looking infeasible. The Santa Barbara's desal plant, as it's currently being recommissioned, would probably not be permitted today based on what we know now about the impacts and environmental harms caused by open ocean intakes. And the feasibility study that would be required today, were the city not grandfathered out of complying with the new state desal policy, would have evaluated subsurface intake and potable reuse options for the actual amount of water to be produced, as well as a combination of subsurface intake and surface intakes. So in conclusion, this study is a real shame and a disappointment for those who sought a sincere assessment of the true range of alternatives and solutions to the death of billions of marine organisms that will be caused by the open ocean intake. I guess those folks will now have to go back to praying for another March miracle. Thank you.
And our last public comment is James Hawkins with Heal the Ocean. James.
James Hawkins with Heal the Ocean. Thank you for the panel for your work on this study. Thank you to Corolla Engineers for their work on this study. I don't have any significant comments at this time. I just want to say Heal the Ocean continues to support the study of potable reuse and investigation of that potential water supply, and we look forward to the June workshop when that will be discussed. So thank you very much.
So, Amy, that's all the public comments we have, unless there are any last-minute ones. Oh, sure. Please, come on up. Can you just say your name and affiliation?
Good morning, Steve Nipper. I'm sorry I don't have a written out presentation here for you, but as a local business owner, native of Santa Barbara, and someone who pays the city water rates here, I'm not particularly in favor of changing what we have going on here. It seems like a huge waste of money. The possibility of permanently changing our waterfront and also increasing our water rates. I'm already paying about $70 for each 1 unit of water I use at my office, and I don't think any of this is going to be at no charge. So, thank you.
Okay, so this concludes the public comments. Amy, I just want to remind you that we will be accepting public comments that are written for 1 week after this. So between now and next, I guess it was Thursday? Wednesday. And so we'll, oh, I'm sorry. 2 weeks. I've been corrected by Suzanne. It's right here behind me. So we will have that up on our website. We'll email that out to our contact list, but so there'll be 2 weeks for written comments, and so potentially there'd be some that would come through that process.
Okay, very good. Unless there's anything else, Jeff, we will adjourn the open session.
So let me ask Suzanne, is there any more slides? Great. So again, this is our reference to our resources where you can find all the documents and updates. And again, a 2 weeks for the comments in from the public. As Tom from Corolla mentioned, there will be a third workshop in a June timeframe. Information will be sent out as we get closer to that. The panel will be developing a panel report based on this meeting. That panel report will be made public in a few weeks and will be posted to the website, and we can notify people, folks on that as well. So, Amy, anything else that you would like to say from the panel point of view?
No, I think we're good.
Okay, Tom or Joshua? Okay, well, thank you all for coming. We do appreciate it.